Hello, I'm Mike McCulloch. Today I'd like to talk to you about Newton's gravitational constant again, but with a bit of a difference this time. I'm going to focus on how it's measured and what has been found out by experiment. So ever since Cavendish, at Cambridge, the gravitational constant has been measured using a torsion, what's called a torsion balance. So what they do is they suspend a wire from a fixed point, they attach a dumbbell to that wire, and then they have weights at either end of the dumbbell, which are then attracted to other masses that they can introduce, known masses. So in this example I've shown here, there are actually two crossed dumbbells, so you've got four masses there. And then what you do is you apply known masses, put them close to the first ones, and this means that they will gravitationally attract, and the whole contraption will rotate very slightly. Now what they do is they measure the wire very carefully before with known masses and known torques, known forces, so that they know what amount of twist in a wire equals which force, and so they can work out the force that they're getting from a particular mass and set of distances. So if you look at Newton's gravitational law, you'll see that if we know the force that we have observed, we know the masses that we're introducing, we know the distances apart, you can revert this, you can put this equation in terms of g, express it in terms of g, and you can calculate g from these known observations. And this is what they've been doing for 200 years or so. And recently the tests have become extremely accurate, very accurate indeed, because they take all sorts of things into consideration, and people like Schlaminger from Germany and Quinn from Britain do this very well. But what they've noticed is that they all get a very accurate measure for g, and the error bars in their measurements are quite small, but when they compare their measurements they disagree, and they disagree beyond the error bars. So this can't be right. So what this means is that each time they do the experiment they work out an exact value of g, which is really accurate, but then they all work out a different exact value of g. So there's obviously something not right here. So I started to think about this in terms of quantized inertia, and you can kind of explain the differences they're getting with it. So what you do is the kind of idea is that what they're missing is an effect on inertial mass, because if the inertial mass of the balls changes for whatever reason, then that will appear in the data. So if the inertial mass reduces for some reason, then the balls will be attracted more than you would expect, and so you would infer a higher value of g. But actually it's not a higher value of g, it's just a lower inertial mass. So how can we test this? Well, we can write the Newton's second law and Newton's gravitational law as is shown here, and then in the second law we use quantized inertia to redefine the inertial mass. So we can put in that term 1 minus 2c squared over a theta, where theta is a Hubble distance. And you can rearrange this and make a tiny approximation as well, and if you arrange it you get an expression like this, and we get a term like this one. So the acceleration you should see should be gm over r squared times 1 plus, and in brackets 1 plus 2c squared over a theta. Now in this second term, this a is the acceleration of the balls. So we would expect there to be some change made, whether the balls have a small acceleration because they're small masses attracting each other, or a large acceleration with larger masses attracting each other. And so if you take this derivation a bit further, you get this, and you can see the mass of the balls is on the bottom of this second term on the right hand side. So that means that quantized inertia should mean that if you have a system with very low acceleration, so very small balls attracting each other, then you should get a drop off of inertial mass and g would appear to be larger. But if you have a system with very large masses and a very high acceleration, or well, not a high acceleration but a much higher acceleration than the other one, then you should get a less of a change of inertial mass, less of a reduction of inertial mass, and so a more normal value for g. And by looking at the difference between the experiments of Schlaminger, who used a very heavy amount of mercury in his experiments, and the smaller ball experiments of Quinn and Speake, for example, I've managed to show that this does in fact happen. So yeah, this is a nice agreement, and it suggests that these variations in g may be due to changes in inertial mass. And there are also other observations as well that have been made by John Anderson that show that the value for g in these experiments, and perhaps inertial mass as well, is varying with a 6-year period, which is very interesting. Okay, so g may not be as constant as we think it is. Okay, I hope you've enjoyed this short, and I look forward to talking to you next time. Goodbye.